It's infinitely long. Okay, lambda to infinity. Okay, so I think this is a example for the dispersion curve. Okay, yeah. Now let's look at another case. Yeah, for wave propagation, it's very close to the physics. So you need a lot of mathematics, formula, equations, theory to write out. So you solve, it's kind of applied mathematics, right? Yeah, a lot of equations. Okay. Now let's characterization of powers by Fourier transform. Okay. So another topic. Powers by Fourier transform. Let's look at. So first, let's look at the narrow band powers. Narrow band powers. Okay. 再带宽的啊。So this topic, let's study a case. Consider the forced motion of semi-infinite 半无限 semi-infinite string on an elastic foundation. Okay, so we will continue the previous governing equation. Okay, and previous result. With a boundary condition, what? At the end, semi-end, x equal to 0, and anytime t is under a dynamic forcing. Okay, so this is a semi-infinite ring, a string on elastic foundation. Okay, and initially, so under T tension force with a material property K, density rho, and under initial, and this is a YXT diffraction. At this x equal to 0, I have initially I have FT oscillation about the diffraction. This is my boundary condition. Okay, then I will study the propagation problem of this semi-infinite. Okay, for t, larger than infinity, smaller than infinity. Okay, so ft, if you draw, certainly it's time domain. You say, okay, I can show before smaller than is 0, and suddenly I have anyway waveform. This ft. Okay, any shape. Okay, this is my boundary condition. At this is x equal to 0 means initially all the time. So this case, my boundary condition is changing. Okay, changing by ft. It's continuous. Input some energy into the system. So let's see what happened. Okay. Now, all right. Then we apply the Fourier transform. Fourier transform in time. Y bar x omega equal to 1 over square root of 2 pi minus infinitive yxt exponential I omega t dt. Okay? So I say no matter what kind you like to use the minus as a Fourier transform forward. Okay. It's quite up to you. All right? And this is can be nothing or 2 pi or 1. Depends on what kind of inverse form you define. Right? So, if I define this called the Fourier transform, then my governing equation, then the governing equation y xx minus 1 over c0 square y tt equal to k over ty or minus equal to 0 becomes y bar xx plus omega square over c0 square y bar minus k over t y bar equal to 0. So become okay. Then I rearrange this, become a y bar xx plus gamma square y bar equal to 0, and gamma square equal to omega square over c0 square minus k over t. Okay? So I have to solve this ODE. After we transform this governing equation, partial differential equation, after we transform about one parameter variable, then we can degenerate to the ODE, from PDE to ODE. Okay? All right, so we solve it. Yeah. Certainly, if you solve this problem in frequency domain, your boundary condition also has to be changed to in frequency domain. So my boundary condition becomes what? Y bar 0 omega equal to f bar omega as 1 over 2 pi, do the integration ft into the transform formula I omega t dt. Then you will do for any given this form, you can do this and you can get the transform f bar, right? Yeah. For any given, you just do it. Yeah. Now, the solution of this equation, we have y bar equal to a e I gamma x plus b e minus I gamma x. All right? Then for this solution, your y xt will be Fourier's inverse about the y bar. Y bar x omega. Is that right? We do the change of t. Then it will, however, it will become 1 square 2 pi minus infinity to infinitive y bar x omega exponential minus I omega t d omega. Then I can change back to time domain. All right? What I want to let you know is, okay, I put here. Here is the minus sign here. So this will be A E I gamma x plus B E minus I gamma x. All right? And yeah. And this will be do something 2 pi minus infinity to infinitive. Then we'll have A E I gamma x minus omega t something plus B E minus I gamma x plus omega t. And d omega. Right? Right? Okay? So this one means, this term mean leftward propagating. Alright? And this is a forward, a rightward. If I define this as x and yeah, and this is x equal to 0. So this is a leftward, rightward propagating. Okay. So for this problem, if my boundary condition is I have a y0t as pt, and all the signals supposed propagating to the right, right? Do we have any solution in that direction? No. No. So this b has to be 0 in force to be 0. Otherwise, you will have some solution not meaningful because no refraction. This is infinitive, right? I give a signal from the end. Suppose all the waveform is propagating to the right. No refraction. That means no leftward propagating wave. So this b should enforce to be 0. So that's why my solution will be 0 required for this one. All right? Yeah. All right. So so my my y bar equal to A E I gamma x, and y bar at 0 t equal to 0 omega equal to f bar omega, right? This one, right? This equation. Okay. And this is a given. Given this, you can get f bar, and that will be the y bar 0. Then, so this equal to a e I gamma 0 equal to a. So a equal this. So my y bar x omega equal to f bar omega e I gamma x. Okay. Okay. Okay, I think let me stop here. Yeah. Okay. Tomorrow, let's continue.